In the 1980s, a new mathematical model of theoretical physics called string theory emerged. It showed how all the different subatomic particles known to science could be constructed by hypothetical one-dimensional strings, infinitesimal building blocks that have only the dimension of length but not height or width. These strings vibrate in multiple dimensions and, depending on how they vibrate, they might be seen in three-dimensional space as matter, light, or gravity. In string theory, every form of matter is said to be the result of the vibration of strings. However, for string theory to be mathematically consistent, the strings must live in a universe with 10 dimensions. String theory explains our perception of the universe to have 4 dimensions, 3 space dimensions and 1 time dimension, by imagining that the extra 6 dimensions are curled up to be so small that they can't be observed day to day. The technical term for this is compactification. These dimensions are usually made to take the shape of mathematical objects called Calabi-Yau manifolds. 5 major string theories were developed and found to be mathematically consistent with the principle of all matter being made of strings. Having 5 different versions of string theory was seen as a puzzle. Chapter 3. There are 12 propositions common to all mutakalemim, however different their individual opinions and methods may be. The mutakalemim require them in order to establish their views on the 4 principles. I shall first enumerate these propositions and then discuss each separately together with the inferences which may be drawn from it. Proposition 1, all things are composed of atoms. Proposition 2, there is a vacuum. Proposition 3, time is composed of time atoms. Proposition 4, substance cannot exist without numerous accidents. Proposition 5, each atom is completely furnished with the accidents, which I will describe, and cannot exist without them. Proposition 0, accidents do not continue in existence during 2 time atoms. Proposition 7, both positive and negative properties have a real existence and are accidents which owe their existence to some causa efficiens. Proposition 8, all existing things, that is, all creatures, consist of substance and of accidents, and the physical form of a thing is likewise an accident. Proposition 9, no accident can form the substratum for another accident. Proposition 8, the test for the possibility of an imagined object does not consist in its conformity with the existing laws of nature. Proposition 12, the idea of the infinite is equally inadmissible, whether the infinite be actual, potential, or accidental. That is, there is no difference whether the infinite be formed by a number of coexisting things or by a series of things, of which one part comes into existence when another has ceased to exist, in which case it is called accidental infinite. In both cases, the infinite is rejected by the mutakalemim as fallacious. Proposition 13, the senses mislead and are in many cases inefficient. Their perceptions, therefore, cannot form the basis of any law or yield data for any proof. Quantum theory is a revolutionary framework that governs the microscopic world. It reveals a reality vastly different from our everyday experiences. At the subatomic level, particles like electrons and photons behave in bizarre and counterintuitive ways. They can exist in multiple states at once, a phenomenon known as superposition. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels. It's a realm where the classical laws of physics break down. Instead, we find a world governed by probabilities and uncertainties. The act of observation itself plays a role in determining the outcome of experiments. Imagine a coin spinning in the air. Before it lands, it exists in a superposition of both heads and tails simultaneously. This is analogous to the state of a quantum particle before it is measured. Only upon observation does the particle choose a definite state. This is the strange world that quantum theory reveals. The development of quantum theory began in the early 20th century. Scientists like Planck, Einstein, Bohr, and Heisenberg contributed to this groundbreaking field. Their work overturned classical notions of physics and opened up a new understanding of the universe. It continues to be a vibrant area of research today. Some experiments have explored the idea of reversing the flow of time at a quantum level. This involves manipulating the state of particles to simulate a backward time evolution. By carefully controlling quantum states, researchers can create conditions where particles appear to move backward in time. These experiments challenge our understanding of time and causality in the quantum realm. String theory posits that the fundamental constituents of the universe are not point particles, but rather tiny vibrating strings. These strings can oscillate in different modes, which correspond to different particles, and require additional spatial dimensions beyond the familiar three. When light passes through a prism, it splits into its constituent colors, demonstrating how light can be decomposed into different wavelengths. Imagining light strings as the fundamental components of reality allows for a creative representation of how different dimensions interact. The absence of light can be viewed as a representation of the vacuum state in quantum field theory, where fluctuations occur, leading to the spontaneous creation of particles and antiparticles. Each color can represent a different dimension or reality, with their interactions creating unique visual and experiential phenomena. The merging and separation of colors can illustrate how dimensions influence one another, akin to entangled particles in quantum theory. By visualizing light strings in various colors, we can explore how different dimensions might interact and represent the complexity of our universe. Another fascinating concept in quantum mechanics is the quantum loop. This describes how particles can transition between energy states instantaneously without traversing the intermediate space. When an electron in an atom absorbs or emits a photon, it jumps from one energy level to another in a discrete manner. This phenomenon has profound implications, suggesting that energy changes in quantum systems are not gradual, but occur in sudden discrete steps. Understanding quantum leaps helps us grasp the non-continuous nature of quantum mechanics and the unique behavior of particles at the microscopic level. The interplay between time, being, and the manifestation of movement touches on profound concepts in both quantum physics and metaphysics. In quantum physics, the idea of a quantum leap without a distinct time resonates with the concept of superposition, where particles exist in multiple states simultaneously until observed. This ties into string theory, where the fundamental constituents of reality are one-dimensional strings vibrating at different frequencies, creating the particles and forces we observe. The hoe of being could be seen as a metaphor for the underlying fabric of reality, where the relationship between time and being is not linear, but interconnected in a complex, multidimensional tapestry. This aligns with the philosophical notion that time and existence are deeply intertwined, and that the movement and change we observe are manifestations of deeper underlying principles. The beginning of everything is reminiscent of the Big Bang theory in cosmology, where the universe emerged from a singularity, a point of infinite density and temperature. In this context, the movement of a thing could symbolize the expansion of the universe and the unfolding of space-time. How do these concepts integrate with our understanding of consciousness and the philosophical interplay of light and darkness? Superposition is one of the most mind-bending concepts in quantum mechanics. It suggests that a quantum system can exist in multiple states simultaneously until measured. This challenges our classical intuition, where an object can only be in one state at a time. Think of a particle being in multiple places at once. Another strange phenomenon is quantum entanglement. This occurs when two or more particles become linked in such a way that they share the same fate, no matter how far apart they are. If you measure the state of one entangled particle, you instantly know the state of the other, even if they are light years away. This interconnectedness is truly remarkable. Quantum tunneling is yet another example of quantum weirdness. It's the ability of a particle to pass through a potential barrier, even if it doesn't have enough energy to do so classically. Imagine a ball rolling up a hill but somehow appearing on the other side without ever reaching the top. This is analogous to quantum tunneling. These quantum phenomena have profound implications for our understanding of reality. They suggest that the universe at its most fundamental level is far stranger and more interconnected than we previously imagined. Exploring these concepts opens up new possibilities for technology and our understanding of the cosmos. Just as Vitruvius's work on human proportions reflects a philosophy where human beings are the measure of all things, the idea of a quantum leap in philosophy could refer to a significant change or advancement in thought. The genesis of today's philosophy of reform can be seen as a foundational shift in societal values and structures. Combining these concepts, we infer a philosophy that values significant foundational changes centered around human experiences, aiming for a harmonious and balanced society. The Many Worlds Interpretation, or MWI, is a fascinating and controversial interpretation of quantum mechanics. It proposes that every quantum measurement causes the universe to split into multiple parallel universes. Each universe represents a different possible outcome of the measurement. In one universe, the coin lands heads; in another, it lands tails. MWI suggests that all possible outcomes of a quantum measurement are realized in some universe. This means that there could be an infinite number of parallel universes, each representing a different branch of reality. It's a mind-boggling concept that challenges our understanding of what it means for something to be real. The implications of MWI are profound. It suggests that our reality is just one of many possible realities. Every decision we make, every quantum event that occurs, could be branching off into new universes. This creates a vast and complex multiverse, a tapestry of interconnected realities. While MWI remains a controversial interpretation, it offers a compelling explanation for the strange behavior of quantum systems. It removes the need for a special role for the observer in collapsing the wave function. Instead, all possibilities are realized, each in its own separate universe. Quantum leaps refer to the sudden transition of electrons between energy levels in an atom. These transitions involve the absorption or emission of photons. When an electron absorbs a photon, it moves to a higher energy level. Conversely, when an electron emits a photon, it drops to a lower energy level. These energy levels are discrete, meaning electrons can only exist in specific quantized states. This concept contrasts with classical models, where energy levels are not quantized. The quantized nature of these transitions is observed in atomic spectra, where each spectral line corresponds to a specific energy transition. The Bohr model of the atom was one of the first to incorporate quantum leaps, with electrons in defined orbits around the nucleus. Modern quantum mechanics, however, describes electrons as existing in probability clouds rather than fixed orbits. The interaction of photons with electrons is fundamental to many processes in physics and chemistry. This interaction is complex and mathematically challenging, involving the principles of quantum mechanics. Understanding quantum leaps offers a promising avenue for unifying the fundamental forces of nature and understanding the universe at its most fundamental level. Section 5. Controlled quantum jumps. Recent experiments have shown that quantum jumps can be monitored and even reversed. By catching a quantum system mid-jump, researchers can control the process, challenging the notion of randomness in quantum mechanics. These controlled quantum jumps are a fascinating and groundbreaking concept. These quantum jumps are not directly observable in our everyday experience, but they are essential for the consistency of the theory. They are thought to be manipulated at a subatomic level. Imagine a lab setup viewed from a distance. It appears as a complex setup. However, upon closer inspection, we see that it has intricate details, crucial for the experiments. Similarly, the controlled quantum jumps are thought to be manipulated at a subatomic level. These controlled jumps play a crucial role in the dynamics of quantum systems. They influence the way quantum systems behave and interact, and they may hold the key to understanding the fundamental forces of nature and the origin of the universe. Section 6. The dual nature of light. Light exists in a state within parts of relationships, exhibiting both wave and particle behaviors. This dual nature is a fundamental concept in quantum mechanics and the philosophy of the hidden world on the visible. Light can propagate like a wave, showing interference and diffraction patterns, yet it can also interact as discrete packets of energy called photons, connecting different forms of reality. As a wave, light has properties like wavelength and frequency, forming a complex golden relation. The wavelength determines the color of light, while the frequency determines its energy, reflecting the interconnectedness of all reality. Red light has a longer wavelength and lower frequency than blue light, illustrating differentiated degree relations. The speed of light in a vacuum is constant, approximately 300,000 kilometers per second, a fundamental constant in our universe. As a particle, light interacts with matter through the exchange of photons, connecting the smallest parts of reality. Photons are massless particles that carry energy and momentum, forming a bridge between different forms of reality. The energy of a photon is directly proportional to its frequency, a principle that ties into the philosophy of Kabbalah. This particle-like nature of light is evident in phenomena like the photoelectric effect, showing the hidden world on the visible. The dual nature of light is a remarkable example of the counterintuitive behavior of the quantum world, connecting us in strange ways. It highlights the limitations of our classical intuition and the need for a new framework to describe the universe at its most fundamental level. Just as the inquiry into the nature of light can lead us to profound and complex understandings, so too can the exploration of the universe's creation and the principles that govern it. We must tread carefully, as delving too deeply into these mysteries can be overwhelming. Like peering through a crack, we can glimpse the wonders of the quantum world without losing ourselves in its depths. Pause 3S, Section 7, Quantum Time Crystals. Imagine a world where time flows in a loop, a realm where the passage of time does not lead to energy loss. This is the essence of quantum time crystals, systems that exhibit periodic motion in their ground state, essentially time crystals that repeat in time without energy consumption. Time crystals challenge our conventional understanding of time and motion. In classical physics, a system at its lowest energy state or ground state is static. However, in the quantum realm, time crystals display a periodic structure in time, similar to how ordinary crystals have a periodic structure in space. These time crystals are not perpetual motion machines, rather, they offer a unique perspective on time in quantum systems. They exhibit a new phase of matter, one that remains in perpetual motion without expending energy, defying the traditional laws of thermodynamics. The discovery of quantum time crystals opens up a new frontier in understanding the nature of time and its role in the quantum world. They provide a tangible example of how the quantum world can behave in ways that are fundamentally different from our everyday experiences. Time crystals bridge the gap between the abstract and the concrete, connecting us to the hidden symmetries of the universe. They remind us that time, like light, has dual aspects, both linear and cyclical, offering a deeper insight into the interconnectedness of all things. As we delve into the mysteries of quantum time crystals, we are reminded of the vast potential of the quantum world to reshape our understanding of reality. They stand as a testament to the ongoing quest to uncover the fundamental principles that govern the universe. Just as light can exist as both wave and particle, time can flow in ways that challenge our intuition, inviting us to explore the deeper layers of existence. In this journey, we are not just observers but participants in a grand cosmic dance where time and matter intertwine in the fabric of the quantum world. Let us continue to explore these profound mysteries, ever mindful of the delicate balance between knowledge and wonder as we seek to unravel the secrets of the universe. With the understanding of quantum time crystals, we are poised to unlock new realms of possibility, forever expanding our perception of the cosmos and our place within it. Pause 3S. Section 8. Quantum entanglement and time. Imagine two particles so deeply connected that the state of one instantaneously influences the state of the other, no matter the distance separating them. This is the phenomenon known as quantum entanglement. Entangled particles share a state in such a way that the measurement of one particle instantly affects the other, even if they are light years apart. This challenges our traditional notions of locality and causality, suggesting that information can be shared instantaneously across vast distances. Quantum entanglement has profound implications for our understanding of time. In classical physics, events are bound by the speed of light, setting a limit to how quickly information can travel. However, entangled particles seem to defy this constraint, hinting at a deeper, more intricate fabric of reality where time and space are interconnected in ways we are only beginning to comprehend. The phenomenon of entanglement suggests that the concept of time may be more fluid than we have previously understood. It raises questions about the linear progression of time and opens up possibilities for new models of temporal relationships. Entanglement also touches upon the notion of causality, the relationship between cause and effect. In the quantum realm, cause and effect may not be as straightforward as they appear in our macroscopic world. This leads us to reconsider the nature of reality itself, where actions can have instant repercussions across the universe. As we delve deeper into the mysteries of quantum entanglement, we are reminded that our understanding of the universe is still evolving. The interplay between time, space, and entanglement invites us to explore new horizons and question the fundamental principles that govern our reality. By studying entangled particles, we gain insights into the interconnectedness of all things, revealing a universe where everything is linked in a delicate balance. This journey into the quantum realm not only expands our scientific knowledge, but also enriches our philosophical and existential perspectives, reminding us of the profound unity that underlies the cosmos. Let us continue to unravel the secrets of quantum entanglement and time, ever curious and ever open to the wonders that await us in the depths of the quantum world. Section 7. Colors of light, a dimensional analogy. We can use the colors of light as an analogy to represent different dimensions or states of reality. Imagine each color corresponding to a different dimension. Red light could represent our familiar 3 spatial dimensions, while blue light could represent a higher dimension beyond our perception. Just as we can decompose white light into a spectrum of colors using a prism, perhaps the universe itself is composed of multiple dimensions interwoven together. Our limited perception allows us to experience only a small slice of this multidimensional reality, just as our eyes can only detect a limited range of the electromagnetic spectrum. The vibrant colors of a rainbow can be seen as a manifestation of the different frequencies of light. Similarly, perhaps the different dimensions of the universe are vibrating at different frequencies, and our limited senses can only perceive a small portion of this cosmic symphony. By exploring the analogy of colors and dimensions, we can begin to grasp the complexity and interconnectedness of the universe. It encourages us to imagine possibilities beyond our immediate perception and to contemplate the vastness of the cosmos. Section 8. Superpositionality and the invisible reality. The concept of superpositionality suggests that reality is not simply linear and clear, but rather a complex and often invisible state. In quantum mechanics, the vacuum state is not empty space, but a dynamic field where virtual particles pop in and out of existence. Even in the absence of visible matter, there is still fundamental activity at the quantum level. The vacuum state represents the lowest energy state of a quantum field, yet it is far from inactive. This state is characterized by the constant emergence and disappearance of virtual particles. These temporary fluctuations in the quantum fields are a hallmark of superpositionality. These fleeting particles contribute to the energy and complexity of the vacuum. The concept of the vacuum state challenges our classical notion of empty space, revealing a hidden dynamism. It suggests that, even in the absence of matter and light, there is a fundamental and invisible dynamism at play. This dynamism is a consequence of the uncertainty principle and the probabilistic nature of quantum mechanics. The vacuum state has profound implications for our understanding of the universe, suggesting a reality filled with potential and activity. It implies that even seemingly empty space is teeming with invisible potential and activity. This hidden activity can have measurable effects such as the Casimir effect, where quantum fluctuations create a force between 2 uncharged conductive plates. Section 9. Visualizing interconnectedness. Visualizing light strings vibrating at different frequencies can help us grasp the interconnectedness of various dimensions. Imagine these strings as conduits of energy and information, connecting different parts of the multiverse. The vibrations of these strings could represent the flow of information between dimensions. Just as the different colors of light represent different frequencies, perhaps the different dimensions of the universe vibrate at different frequencies, creating a symphony of interconnected realities. These vibrations could be the key to understanding the fundamental forces of nature and the interactions between different dimensions. Imagine a web of light strings, each vibrating at a unique frequency, connecting different points in space-time. This web could represent the interconnectedness of all things in the universe, a tapestry of light and energy weaving together the fabric of reality. By visualizing these interconnected light strings, we can gain a deeper appreciation for the complexity and interconnectedness of the cosmos. It allows us to see beyond the limitations of our perception and to imagine a universe far richer and more interconnected than we ever thought possible. Section 10. Conclusion: a tapestry of light and dimensions. Quantum theory, string theory, and the study of light reveal a universe far stranger and more complex than we ever imagined. From the bizarre behavior of quantum particles to the vibrating strings of string theory and the multidimensional nature of reality, the universe is a vast and mysterious tapestry waiting to be explored. The colors of light, with their different frequencies and wavelengths, offer a powerful analogy for understanding the different dimensions and states of reality. Just as a prism decomposes white light into a spectrum of colors, perhaps the universe itself is composed of multiple dimensions interwoven together. The absence of light, the vacuum state, is not empty space, but rather a seething cauldron of virtual particles, a constant reminder of the dynamic and interconnected nature of reality. Even in darkness, there is activity, potential, and interconnectedness. By exploring these concepts, we embark on a journey of discovery, pushing the boundaries of human knowledge and expanding our understanding of the cosmos. The universe is a vast and mysterious place, and the quest to understand its secrets is a testament to the human spirit of inquiry and exploration. Pause 3S. Section 11. The human blueprint and cosmic proportions. Vitruvius, the ancient Roman architect, once said in his architectural work that the measurements of man are in nature distributed in this manner: 4 fingers make a palm, 4 palms make a foot, 6 palms make a cubit, 4 cubits make a man, 4 cubits make a footstep, 24 palms make a man, and these measures are echoed in his buildings. Pause 2S. If you open your legs enough that your head is lowered by 1/14 of your height, and raise your arms enough that your extended fingers touch the line of the top of your head, you will find that the center of the ends of the open limbs will be the navel, and the space between the legs will form an equilateral triangle. Pause 2S. And below. Tanto apre l'uomo nelle per accia quanto è la sua altezza. Dal nascimento dei capelli al fine di sotto del mento è il decimo dell'altezza dell'uomo. Dal di sotto del mento alla sommità del capo è l'ottavo dell'altezza dell'uomo. Dal di sopra del petto alla sommità del capo fia il sexto dell'uomo. Dal di sopra del petto al nascimento dei capelli fia la settima parte di tutto l'uomo. Dalle tette al di sopra del capo fia la quarta parte dell'uomo. La maggiore lag za delle spalle contiene in sé la quarta parte dell'uomo. Dal gomito alla punta della mano fia la quarta parte dell'uomo. Da esso gomito al termine della spalla fia la ottava parte dell'uomo. Tuxta la mano fia la decima parte dell'uomo. Il membro virile nasce nel mezzo dell'uomo, il piede fia la settima parte dell'uomo. Dal di sotto del piede al di sotto del ginocchio fia la quarta parte dell'uomo. Dal di sotto del ginocchio al nascimento del membro fia la quarta parte dell'uomo. Le parti che si trovano infra il membro. Tu è il naso e il nascimento dei capelli e quel dei cigli ciascuno spazio. È simile all'orecchie e il terzo del volto. Pause 2S. Translated, it means that the length of the outspread arms is equal to the height of the man. From the hairline to the bottom of the chin is 1/10 of the height of the man. From below the chin to the top of the head is 1/8 of the height of the man. From above the chest to the top of the head is 1/6 of the height of the man. From above the chest to the hairline is 1/7 of the height of a man. From the chest to the head is 1/4 of the height of the man. The maximum width of the shoulders contains 1/4 of the man. From the elbow to the tip of the hand is 1/4 of the height of a man. The distance from the elbow to the armpit is 1/8 of the height of the man. The length of the hand is 1/10 of the man. The virile member is at the half height of the man. The foot is 1/7 of the man. From below the foot to below the knee is a quarter of the man. From below the knee to the root of the member is a quarter of the man. The distances from the chin to the nose and the hairline and the eyebrows are equal to the ears and 1/3 of the face. Pause 2s. These measurements are not just a testament to the symmetry and proportion within the human body, but also an echo of the cosmic order. Just as the universe is a tapestry of light and dimensions, so too is the human form a microcosm of this grand design. By understanding these proportions, we bridge the gap between the architecture of the cosmos and the architecture of humanity, revealing the interconnectedness of all things. Pause 2s. As we continue our exploration, let us remember that the quest for knowledge is not just about the vastness of the universe, but also about the intricacies within ourselves. The proportions of Vitruvius remind us that the cosmos and humanity are bound by the same fundamental principles, a beautiful symmetry that connects us to the very fabric of existence. Quantum computing and time travel. Theoretical models in quantum computing explore the possibility of simulating time travel. These models use quantum bits or qubits to represent and manipulate time states, potentially allowing for computations that mimic time jumps. Pause 2s. Imagine a world where the boundaries of time are not fixed. Quantum computing, with its ability to process vast amounts of data in parallel, opens the door to such possibilities. Unlike classical bits, which are either 0 or 1, qubits can exist in a superposition of states, enabling them to perform complex calculations that were once thought impossible. Pause 2s. Researchers have proposed models where qubits could be used to simulate time travel scenarios. By manipulating these quantum states, it might be possible to create a computational framework where time behaves differently, allowing for the simulation of time jumps. This doesn't mean we would physically travel through time, but it could provide insights into the nature of time and how it can be manipulated at a quantum level. Pause 2s. One fascinating aspect of this research is the potential to solve problems that are currently intractable. For instance, certain cryptographic algorithms that would take classical computers millennia to break could be solved in mere seconds with quantum computers. If time manipulation through quantum computing becomes a reality, it could revolutionize fields like cryptography, optimization, and even artificial intelligence. Pause 2s. The implications of quantum computing and time travel are profound. They challenge our understanding of reality and open up new avenues for exploration. Just as the human blueprint and cosmic proportions reveal the interconnectedness of all things, so too does quantum computing bridge the gap between the theoretical and the practical, offering a glimpse into the future of technology and our place within the cosmos. Pause 2s. As we stand on the brink of this new frontier, we are reminded that the quest for knowledge is a journey through both space and time. Quantum computing and its potential to simulate time travel is a testament to human ingenuity and our relentless pursuit of understanding the universe.